we might start. And this COP, thank you so much for joining us. This has been a journey for me in my career. I first learned about shrinkage when I used to work with Voot back in 1988 at CSIRO. And then I started working in the concrete supply industry in the opposition company to Dean and Michael Bowie and Greg Van Ruin. And I used to have an aggregate that used to shrink 100 microstrain more than Greg's and Dean's aggregate concrete. And so I always used to be on the wrong end of specific. And then I started to discover this thing called shrinkage and this AS 1012 part 13 number. And then what happened was I used to find that it's a 56-day number, but all the problems were occurring at 56 hours, at which point I started to tear my hair out and try to do work in this area to try and understand things. And what is really terrific is that over the years, there has been a lot of work. The thing, though, is that with this, and this is a hot topic because this is where we were talking earlier about how we talk about cracks and crack control and all of this sort of stuff. So it's a massive issue for us in the industry, and there's been a lot of good academic work done. I guess the big challenge that I see at the moment is that we're translating that knowledge into standards, because I actually think the standards need to sort of come up a way to do that, to actually address this issue. Having said that, the great thing about SmartCrete and this work is that we have actually got BG&E has actually funded some work at SmartCrete, and I know that we also have Queensland Main Roads in the background. So what we have today is some of our early results from this work. The work is being done at UTS with through Arno Castell. Voot, you've got your hand up.
Yes, Jack, thank you very much for the introduction. May I propose that we acknowledge Professor V.J. Rankin, who gave us the privilege to join this community of practice.
Certainly. Thanks, Voot. That is absolutely correct. As I said earlier, sorry, Voot.
And that is to make sure that Professor Rankin doesn't ask any difficult questions to us.
Fantastic. So thank you for that, Voot. That's very good. What we've got now is that in terms of this topic, we've got two presentations, one by Greg Van Ruin from BG&E, who's worked in this area for a very long time. And the second is by Arno Castell, who's actually running this research at UTS. So what I'll do now, if it's okay with everyone, is to hand over to Greg to sort of set the scene for us, from which Arno can come through. Greg, over to you.
Well, thanks very much, Dak. I'm going to attempt the screen share now. So hopefully everyone can see.
Yeah, all good.
That presentation. Excellent. So yeah, my job today is basically to take you through some background and why we want to do this work and what it's all about. So I guess we all know concrete cracks and the old saying, all concrete cracks. But concrete's actually really subject to volume change and strain, and cracking comes about because the strain is restrained and held in place. So I suppose what shrinkage is, it's the volume change in concrete. There's quite a few mechanisms, and I guess the work today, we're not really focused on thermal contraction and shrinkage. We're really talking about some early age and drying shrinkage. We typically talk about early age or plastic shrinkage in the first 24 hours or maybe a little bit more, depending on whose work you're looking at, and then drying shrinkage being the longer term reduction in volume through loss of free water in the concrete mix. So slabs on grade probably still make up, well, we think about 70%, but most of the concrete placed. and really come down to problems with unplanned cracking. I think there's a little chat earlier about planned cracking is good cracking and unplanned cracking is bad cracking. And so the joints don't always work. And we relate this to a concrete problem and drying shrinkage. Clearly, as discussed already, the data we get doesn't really match a lot of our field observations. And from my time in a concrete supplier, I'd say dealing with complaints, if you did a Pareto chart of crack complaints, really plastic cracking followed by longer term shrinkage cracking make up, you know, at least 75% of the types of complaints that concrete places or concrete producers face every day. So what do the standards have to say about this? And we have 3600, and it provides some calculation of shrinkage in concrete. It provides some numbers based on where you are in Australia and refers to the AS 10-12-13 test, which is the drying shrinkage test. And the standard does try and account for early age autogenous shrinkage, some basic shrinkage strain, and volume reduction. There's a fair range around Australia. The codes talk about some typical values, but in certain parts of Australia, shrinkage can vary quite widely from different aggregates. And the test also talks, well, the standard talks about a plus or minus 30% range. I guess the key thing though is the aggregate doesn't shrink much. And it's the paste in the concrete that shrinks. So the drying shrinkage is a 56-day test rounded to the nearest 50 microstrain, and to all normal cast concrete needs to fall below 1000 microstrain. Now, the origins of the test are really around selection of aggregate and ensuring you have a stable aggregate in the concrete, less so about the actual concrete performance. And some key points are that, you know, the shrinkage we're measuring in the shrinkage test is after 7 days curing, and then it undergoes 56 days of drying. So it's 63-day-old sample. And has a look at that. Again, trying to improve shrinkage through selection of a type SL cement. There's a 750 microstrain limit for that. So as you can see, typically in those standards and the methods, the allowance for shrinkage is actually quite high comparative to numbers you may see in a specification of less than 600 being quite commonly specified to get a lower shrinkage or try and control cracking. So because of that, there's a tendency to want to put a tight shrinkage specification or requirement in a document to encourage, I guess, cracking to happen the way you want it. Great picture there when you take a piece of unreinforced concrete and you give it a decent saw cut, the crack will happen in the cut. But this doesn't always really work in practice. It's quite common to see cracking happen in an unplanned way. And the movement clearly occurs a lot earlier than what we're thinking in the standard, and I'll show you a little bit of that in a little bit. So from the standard, it doesn't take into account any restraint or shrinkage that may occur a lot earlier in the concrete, and specifying or requiring lower shrinkage doesn't mean lower cracking. So obviously a great topic for further research, and just as a lead into where we're heading, some work done a few years ago by University of Queensland on a large post-tension floor out here in Queensland. And this floor was strain gauges were installed. And when we have a look at the results, the red line. So I suppose it's important to start looking at these dotted lines here are the prediction from the standard from 3600, and we can notice straight away that a lot of the joint opening and the movement becomes sort of 8 to 10 hours after placement. And then after about 160 days, it's fairly constant. You're really just measuring thermal effects. There's more joints opening up more quickly in external pavements, but a key thing is that this behavior doesn't match the predicted behavior. What this research found is that there's a lot of benefit to slowing or stopping early evaporation, and that predicting shrinkage strains in real life was really difficult because of a number of things, including material properties, the environment, and construction practices. And there's no real link at all between the drying shrinkage and the movements measured on site. So where to next? Clearly, we need more research on this early behavior, and we need to understand it, and we need better models that reflect the conditions, and we need to identify and find some of these drivers of what's causing these issues. So the advice in the interim till we see Arno's presentation is that, managing the curing and the early age is really important to limiting cracking, and really the shrinkage test is not the mechanism to control cracking in your concrete. So thanks for that. I hope that sets the scene for everyone on why this is important research. So thanks. And over to Arno.
Thanks very much, Greg. Yeah, that's really set the everything for my presentation. Very grateful. Should I go ahead?
Please do, Arno.
Okay, I share my slides.
And while you're doing that, I'll just say that, look, we'll have opportunities for questions afterwards, and yeah, we'll just defer till then. So please go ahead, Arno.
Can you see my slides?
Yep,
Yes.
all good.
Perfect. Well, thank you very much for having me today to talk about this project, this smart grid project, named Refining Design Deformation Predictions by Improving Concrete Volume Stability Assessment. There's different aspects that are included in this project. Long-term deformation is included, but today I will really focus on early edge cracking, which is consistent with Greg's presentation. Just a few words about me. I started my early academic career in France, in southwest of France. The name is Toulouse, so it was University of Toulouse, and it's a very famous part of France for cheese, duck confit, and amazing wine. So I recommend anyone to just visit the region. It's very nice. So the lab I was working is the durability of construction material lab. So most of the colleagues, including myself, were expert in really durability of concrete. So corrosion of reinforcement, chloride, sulfate, and so on. It's also famous for Airbus industry. That's where the big planes are built in France. I moved to Australia in 2012. I joined the UNSW, where I had the privilege to work with Professor Ian Gilbert, who is very famous for his work on creep shrinkage and concrete cracking. He's basically the one that created and implemented the models for shrinkage and creep in AS3600. So an important project what we had together by combining durability and cracking was that ARC linkage grant. You can see shrinkage, cracking, self-healing, and corrosion of reinforcement in blended cement concrete. I have to acknowledge that I've been learning a lot about shrinkage and creep by working with Ian. It was a great pleasure. And then in 2019, sorry, it was a mistake. UTS is August 2019. So that's when I moved from UNSW to UTS. So back to the topic. So the topic is consistent with what Greg just presented, and we're focusing on restrained shrinkage-induced concrete cracking, particularly on slabs where thermal effects are not that important. So it's one of the assumptions. Today, I will not include anything relating to thermal cracking. And the first assumption you can see at the top is we are really interested in that period up to 7 days after the pour of the concrete. So those cracks are really bad cracks. They're not planned, and there's no way basically to control the crack width. And we know that corrosion of reinforcement in cracked concrete is based on that assumption that we keep the cracks width small. Then self-healing of concrete is there to basically prevent corrosion to happen. So if you have wide cracks, that doesn't work. So those are really bad. What is available for engineers and designers to control the risk of restrained shrinkage, induced early edge cracking in Australian standards? So Greg already talked about it. I'm just getting back to the two tests, basically. The tests we have for concrete. We focus on concrete. So the 10, 12, 13 drying shrinkage, where specimen are stored at 23 degrees, 50% relative humidity. And yes,
Arno, sorry, you've got on my screen, there's a little window that says you're sharing your entire screen. Is it possible so you can move that? Because that's just in front of, beautiful, thank you.
Yeah. So that test is organized such as is the first, basically the first 24 hours specimen are in the molds, the demolds, and they spend 7 days in the water. And then the first time we get a measurement of shrinkage, basically is day number 9. So it's basically too late. It's after that period we are interested in of the first 7 days after the batching of the concrete. So that's a problem. It's not timely, let's say. It will be easy to fix it. It's just about changing the standard and say we start measuring after 24 hours, and we change the name from drying shrinkage to total shrinkage. But at the moment, it's not. I agree what Greg just said. It's not really useful to control early edge cracking because we're measuring a long-term shrinkage. So that's the first problem with what is available to engineer at the moment. Second tool available are the AS3600 models, one for creep, one for shrinkage. Shrinkage includes drying and autogenous shrinkage. Those models were, as I said, developed by Ian Gilbert quite a long time ago. There's some revisions that were implemented in 2017, but the models are still focusing only on general purpose concrete, so there's no SEM effect included in there. And one of the statement that Ian was always providing to me is, well, the main purpose of those models is actually to predict the final shrinkage strain, not really what happened at early edge. So don't be surprised if when using the models, you're not getting a good correlation with the early age shrinkage, just because the models weren't calibrated and developed for early age. So that's important, and it's again just showing that the models we have in the standards, they're not there for early age. They've been developed for long-term shrinkage. So that's a problem for what we are interested in today. So if you do, that's just a test result. So I'll start to talk about test results from the CRC project, where we try to look at different concrete here. So we have, that's a 32 MPa concrete. There's several of them. There's the 0 is no SEM, then 30% fly ash, 40% slag, 60% slag, and see how it's basically influenced, the SCM content is influencing shrinkage. Here, everything from now, everything I will be showing is a shrinkage where the measurements start at day 1, not day 7, and they're stored here in a standard condition. So what we can see is that at long term, yes, there's a difference, 20–25% for concrete with SCM. Not much difference at early age. Well, if I could zoom, you will see a difference, but it's not as much as for long term. So yeah, that's it's already good to know. We're not seeing a lot of influence of the SCM for early age, for that example at least. And now, Greg mentioned already that we are doing tests in standard condition, 23 degree, 50% humidity. How is that reflect what happened in the field? The only thing we can do using the models, ES3600, is to include that K4 coefficient, which is the, relating to the environmental condition, where there's 4 of them, arid and interior. If you compare those two, interior will be close to the standard condition, something around 23 degrees, 50% humidity. Arid will be much drier and hotter, maybe 35 degrees, 20% humidity. So a very different climate, but the value of the K4 coefficient is not that different. It's 0.7, 0.65. So it's basically, according to the model, there's not much difference in terms of shrinkage, depending on those two standard, environmental conditions. But keep in mind that this is a model for long-term shrinkage, not for early shrinkage. Okay, so we did a test, a simple test. We had specimens, the same specimens. Some of them were in standard condition, 23 degrees, 50% relative humidity. And another set of specimens were stored in a different room with a temperature of 38 degrees and only 20% relative humidity. So very different exposure condition, let's say. A good way to basically assess how severe is the exposure condition is the water evaporation rate. Everybody knows this chart. So the water evaporation rate for standard conditions, we try to assess as well the effect of the wind speed, but I won't talk about that today. You see the fans here. So here there's no wind at all included. So if we compare the water evaporation rate at 38 and 23 degrees, it's roughly almost 4 times more water evaporation rate. So question, how is that influencing shrinkage? So that's just one example of test result we had. So that's still a 32 MPa concrete, no SEM, and in red is the shrinkage, total shrinkage at 38 degrees, and in blue is the total shrinkage at 23 degrees. We're measuring after 1 day, so it's total shrinkage, and we see a really important difference at early age, as you obviously between the blue and the red, and it was expected. And then after a while, well, there's not much difference. The two shrinkages are pretty similar. So here I'm presenting the difference between, so it's shrinkage at 38 degrees minus shrinkage at 23 degrees. I'm just talking about that 32 MPa concrete today, and there's 4 of them. One is the 0 is always no SEM. Then there's a 30% fly ash, 60% slag, a 40% slag. So what we can see, so the difference here is in microstrain, but I also added the increase in percentage between the shrinkages measured at the two conditions. So what we can see is that regardless the binder composition, the peak time, so when the difference is maximum, is between 5 and 10 days, which is within the range of early edge cracking time. Not much difference, depending on the binder composition. Composition, it's 70 to 80% increase in shrinkage, which is a lot of difference. At long term, past 50 days, not much difference anymore. All the shrinkage results are merging together more or less. So the conclusion of this test, and it's consistent with the result we have with the 25 MPa or 60 MPa concrete, basically the same. The K4 coefficient in the standard is not able to capture at all the effect of that increase in water evaporation rate that will happen in the film just because it's a hot climate and a dry climate. Okay, that's not possible to do it with the standard. The K4, as I said, is for long-term estimation of shrinkage, and the results are consistent in that case. Because at long term, there's a marginal difference really between the two conditions. So that's again another problem for engineers. We don't have any model that are able to actually predict correctly what happened in the field during that period of time, which is 0 to 7 days. So we don't have a suitable test, and we don't have suitable models for early edge cracking. And there's nothing wrong with that. It's just because those two tools weren't developed and calibrated for the purpose of early edge problem. So what alternative do we have? What are we doing as part of the CRC project? So first thing, just as we do for durability, we know there's concrete that are performing very well against chloride. There's concrete they're not performing well. So it's the same thing for early edge cracking, restrained shrinkage early edge cracking. We need to select a suitable concrete that is likely to resist very well to cracking in that case. So one way is to use the so-called ring test, where you have a concrete ring, which is cast around a steel ring. So when the concrete want to shrink, the shrinkage is restrained by the steel ring. So there's some tensile stresses building up in a concrete ring, and those are sustained, which means there's creep. And creep is in tension, not in compression. And creep is very important because it's actually contributing to reducing a lot the stress level of stress in the concrete. So it's absolutely crucial to account for tensile creep to calculate the stresses. That's what we're trying to do, and calculate the tensile stresses building up in concrete. And the test is pretty easy, because what we only need to do is to monitor, the strain here. What we do is monitor the strain of the steel ring, and when there is a big drop, that means that the ring, concrete ring, is cracking. So we are interested in the time to cracking, and the test is always in the standard condition, 23 degrees, 50% humidity. So I just provide some results here. There's a lot of concrete we've been tested. So you see at the bottom, it's 25, so that's 25 MPa, 32, 40 MPa, 50 MPa, 80, 100 MPa. Red are the one with 30% fly ash, blue, no SEM, and then orange and green are the 40 and 60% slag. So straight away, you can see there's a massive difference in terms of performance depending on the concrete. Here, you can see the rate red dotted line, R7, so it's 7 days. And the criteria will be a concrete that will be performing well, who should not crack before 7 days. And there's a lot of concrete that are actually not passing the test at all. Okay, most of the concrete are not, just few concrete that can pass that test. I'm not here to discuss the detail of each mix design.
No, sorry, I'm just getting some inquiry. We are still looking at your experiments simulating hot, dry conditions. Are your slides moving?
It's moving on my screen.
They're sort of frozen on ours.
Okay.
Yeah, sure. I have a question for Greg. In one of your slides, you were talking about the benefit of evaporation retardants. I was wondering if you could elaborate on the different tactics and like evaporation retardants that you're seeing come that are maybe more experimental that are coming into the market. If you have any insights on that.
No, it's probably more general, wasn't really product specific. The key being a lot of that early age movement is related to moisture loss. So, at this point, you'd say any action you take to retain moisture in the concrete would be beneficial. So, that's between early age evaporation and then getting curing in place as soon as practical is probably about the best advice you can give around, minimizing the potential for cracking. And as we know, even sometimes the best practice, you still end up with cracking. It's quite a challenging thing to overcome.
You get a lot of dimensional change at that when the concrete is, here we are. Arno, can you see that? We've lost Arno. Are you there, Arno? Seem to have lost Arno. See if I can call him up.
I might just follow up that comment from. Oh, sorry.
Could you go to that slide and we last stop, please?
Oh, sorry.
Go further, yeah.
Okay. Yep.
No, more later. I mean, go, yeah, more.
I've got a PDF, so
Yeah, go more, yeah. A
Is that
few
better
more, I
now?
think. No, not yet. Yeah, a few more. Yeah.
Arno
Okay,
is
this one, yeah.
reconnecting, so
Okay.
he's basically he's offline, but he's actually coming back on again. I don't know what's happened at poor UTS, but not only did we lose Arno's slides, we've now lost Arno, so hopefully he's reconnecting back.
okay.
Can you go to the next page, please? Yeah, so we know what is the next page is. Yeah. Okay, alternatives. Okay.
Arno, are you back?
I am back.
Okay,
That's good.
I'll pass
Okay.
back to you.
Okay.
So yeah, no, we didn't see this slide. Yeah, this is where we, couldn't see the beginning of where we couldn't see.
From that, yeah. So
Yeah, from that.
before that was what we have available, so that everyone could see that.
Yes.
Yes.
Mhm.
So now next step is what solution we can propose, or at least what solution we're working on in this project. So alternatives. So next slide, please. So you probably heard me talking about that ring test. So I will
Yes.
be brief. So that test is really about testing the performance of concrete, specifically targeting early age cracking, just like we do with other durability tests. And what we try to look at is how long it takes for the concrete ring to crack in standard condition, 23 degrees, 50% humidity. And next slide, please. So that's an important. We have been testing a lot of different concrete with different strength and different binder composition. The criteria is no cracking before 7 days, so R7. And as you can see, there's a lot of concrete that actually are cracking before 7 days. Only few of them are not cracking. So I'm not going to discuss today because we're going to run out of time, you know, the specificity of the mix design, etc. But obviously, you can see that the fly ash is pretty good for delaying early edge cracking, and slag are not the same at all. So it's more likely to crack early, and increasing the compressive strength of the concrete is not a good thing either. All the concrete at 40, 50, and 60 MPa, except for the fly ash, are cracking. But anyway, so that's just to highlight that, well, there's a lot of difference in terms of performance between the different concrete we're using. And it's better to use a concrete that is likely to perform well. That's the purpose of that type of performance-based testing. Importantly, the concrete that are not cracking within the first 7 days, it's not, it's the one are performing better, but doesn't mean they won't crack in the field. So you have to keep in mind that the testing condition are a standard testing condition. So it's 23 degrees and 50% relative humidity. So if you not include somehow what is the water evaporation rate the day of the pour and a few days following the pour of the concrete, we're never going to be able to control early edge cracking. That has to be part of the you know, the work of engineers to consider case by case what's going to happen the day we're pouring the concrete. Next slide, please. So the in addition to select a concrete likely to perform well, next stage is modeling the actual behavior, the development of stress in the concrete due to restraint shrinkage. And I recommend this document, the Z7, concrete cracking and crack control, that probably everyone knows. Ian Gilbert has been contributing a lot to that document. And that's the base of you know, the modeling we're developing in this project. Next slide, please. So that's there's different type of restraint to shrinkage. Here I will talk about just slab. And the shrinkage is restrained by the reinforcement. You know, the bond between reinforcing bars and concrete is restraining the shrinkage. And the degree of restraint is dependent on the reinforcement ratio. The more bar, the more reinforcement, the more restraint. Okay. Next slide, please. So I'm not going to be getting too much into the detail, but that equation in that document that allow to calculate the stress in tension in concrete due to restraint shrinkage. So the important parameter here is the free shrinkage. So the free shrinkage cannot be calculated using Austrian standard model. You're not going to get anything right doing that. This free shrinkage must include the effect of the field condition, so the water evaporation rate. So we have been working on that for a while now. So we have a way to, well, there's some assumptions that will have to be made. What's going to be the water evaporation rate the day following the pour and a few days after that? But it's possible to include that effect in so the calculation of the free shrinkage. So that's what we do. As I said, concrete creep in tension, it's extremely important. So that's included as well. We have developed tensile concrete creep models that include the effect of fly ash and slag. So pretty confident with this one. The time-dependent increase of the elastic modulus of concrete is very important. And finally, well, that's more the structural design. So reinforcement ratio is governing the degree of restraint. So that's all that needs to be included in that modeling. If we want to be able to compare accurately what is the stress in the concrete to what is the tensile strength in the concrete. Next slide, please. So at the moment, so that's just some simulation results we have done using that model. And the red curve is the tensile strength of the concrete. So those results are experimental results. So you can see the development of the tensile strength of the concrete from day 1 to day 28. And black dotted line is the tensile stress in the concrete, which is building up due to restraint shrinkage. So that's a case of low field water evaporation rate. It's not a severe environment. So that's just showing that concrete is unlikely to crack. Next slide, please. However, by implementing a much higher water evaporation rate, I'm not getting into the detail here about what the value of it or what's the concrete, but what the model tells you is that, well, the stress in the concrete is building up much quicker just because there's more shrinkage. And it's at early age, specific to target early age. That's what we need to do. And according to the simulation result, you're likely to see a crack after 3 days, as the stress is equal to the strength. So that's what the model can do, while still needs a bit of work for the validation. And I think it can be as well very useful to actually design the duration, the minimum duration of concrete curing. By applying curing, there's a good way to limit a lot drying shrinkage. There's still autogenous shrinkage going on. But if you apply curing in that case for 3 or 4 days, it's likely that, well, that will be delayed the increase of the tensile stress in the concrete for 2, 3, 4 days. And when it starts shrinking, drying shrinkage starts again, well, that will leave enough time for the tensile strength of the concrete to be high enough and avoid cracking. So that's a tool that could be very helpful, I think, for designer to to better control large cracking through curing. Because at some stage, if the water evaporation rate is too high, without curing, that's not going to work. It has to be applied. It just be a way to have a better control of what we are doing. Yeah, so that's next slide. That's a strategy. We need tools for engineers that are developed and calibrated specifically for the control of early age cracking. It's a work in progress. And that has to become an alternative to existing Australian standard model and test, just because they're not developed for that purpose. So that it's helpful still, because if you have a high shrinkage at long term, it's likely to be also high shrinkage at short term. But it's just a bit of blind design that's going on at the moment. So hopefully we can develop suitable models and help the industry with that. Thank you for your attention, and so sorry for the problem we had.
Thank you, Arno, and thank you all who alerted us of those issues, and Natalie for stepping in as you did. Look, we've got some time left for some questions. We had that one about the early, the admixture, but look, we've just got the presentations now. We have access to Arno and Greg, so I open up the discussion on anything that's been raised. If you like, Arno, there's one I want to ask you, and that is, how did we get to? Do you know the history of and I thought by some of your ARC and AS36 or the work that you did with CCAA, what's the background? How did this test actually come into the standard?
The test in the standard, you mean the shrinkage test?
Yes, the 10, 12, 5, 13, yes.
No, that's I wasn't born when
Okay, no worries.
I'm not quite sure now.
Michael, please, over to you.
Thanks, Dax. So question is, that graph where you had the different mixes and cracking time, and you had a line drawn across it 7 days, and you found that the fly ash mixes were cracking after the 7-day mark, and many of the other mixes were cracking underneath the 7-day mark. And the comment you made was that the higher strength mixes were more likely to crack before 7 days. I'm guessing that's because with that ring test, it's really a competition between strength development and shrinkage as to when that cracking occurs. And I'm guessing that the higher strength mixes are shrinking pretty early, mainly due to autogenous shrinkage. Could you comment on that, please?
Absolutely correct. That's a problem of the high strength concrete, because we're starting measuring, the shrinkage after 1 day, right? But right after the final setting to 1 day, we found out that there's already a lot of, so there's no drying shrinkage there at that moment. The concrete is still in the molds, protected. And we found out that there's a lot of tensile stress already building up during that period, very, very early age period. Just to give you an example, 80 MPa concrete with a tensile strength at 28 days, that will be 6 MPa. You already have almost 2 MPa there before you demold your specimen, because of high autogenous shrinkage of high strength concrete. This is the opposite for low strength concrete. It's basically almost nothing.
So basically, what Greg and you are both concluding is that you got to cure the concrete and help the strength development and slow down the shrinkage.
Exactly. That's the best way to do it.
Yeah.
In that competition between stress and strength.
Yeah. Thank you.
Okay, so there are 2 questions in the chat which I'll refer to now. Probably the first one is for both of you, is how much autogenous shrinkage is contributing to early age cracking? Greg, you first, and then I'll finish with Arnaud.
Yeah, I think we sort of started talking about that a little bit already, that, the higher cement content, the richer the concrete mix, the more autogenous shrinkage there is. So that gives you this sort of trade-off for the lower strength concretes with more water, therefore higher shrinkage, but then counterpoise with autogenous shrinkage. But yeah, again, autogenous shrinkage probably becomes more of an issue when you're going above 40 MPa concrete, and then you need to consider it. So there are some numbers in guidelines. So there's some values that come out of things like Syria C766, or could give you some numbers to use. But again, looking at the work Arnaud's presenting, these are estimates.
Arnaud, over to you. Autogenous shrinkage and cracking?
Yeah, well, first, just on a positive note, autogenous shrinkage on its own, if there's a good curing and we don't have drying shrinkage, that's not enough maybe to create cracking. So that's, even if it's higher, it's still low compared to drying shrinkage. And well, curing might be enough to avoid a cracking just due to autogenous shrinkage. What's the difference between a 30% fly ash and a 40% slag? Because that's usually, you look at durability issue, 30% fly ash or 40% slag, they're working together, they are all improving the durability. Obviously, it's not the case for early age cracking. That's a wrong way to see it, and that's because of autogenous shrinkage. Because there's more autogenous shrinkage in the slag than in a fly ash concrete. So when combined with drying shrinkage, that's why we see a very early cracks, 4 or 5 days for the slag concrete, and cracking that happened 15 days after for fly ash. So it's important. It's very important. Depend on the grade of the concrete and depend on the binder composition as well.
Okay.
But again, that's why we if we don't want to worry about it, we just use that performance-based test. We just batch a ring and you wait, still tracking, and that tells you if the concrete is is likely to perform well. That's the benefit of the performance-based testing.
So on that, Arno and Greg, so another question is as it is difficult to predict early age shrinkage cracking of concrete, what are the suggestions for asset managers to maintain their concrete assets to maximize service life, considering the potential of shrinkage cracking? That's a big one. Arno, I think we'll start with you, and maybe Greg can chime in later.
So that's all about those good cracks, bad cracks. A good crack is a crack. An example, and it's probably the only example, are flexural cracks, the one in tensile part of slabs and beams that are designed cracked. And the reason is because you can control the crack width. That's the purpose of the standard. And if the crack width is small, first you don't see it. So there's always that aesthetic problem. And if it's small enough, that will self-heal, and it won't create any problem, a durability problem, long-term durability problem. So those are good cracks. Restrained shrinkage-induced cracking is not a good crack because you have no way to control the crack width. So you might end up with a crack width which is a millimeter, and that's not going to self-heal. So that's the problem. And then you're going to have consequences on durability if there's chlorides or any aggressive spaces around that. So the best way to really make sure there's no consequence on the surface life is to prevent that kind of cracking. At least in aggressive environment is crucial.
Correct. So Arno, one of the things that we do, and as I said, Greg and I have been in meetings where you'll sit down and you'll arguing about what I've noticed, particularly with asset managers, and this is just Mr. Alam asked this question, and this is just to sort of like tease this out, where the road authority or whoever will actually specify a maximum crack width, and it could be as small as, or design crack width, which could be as small as 0.2 millimeters. And I know that it becomes really difficult to work out, well, what does that mean in design? And then, which means that just a whole lot of reinforcement. And then what does it mean in construction? What's your thought on that, Arno? Is that something that is a good strategy?
Well, it's limiting crack width is essential. That has to happen after the value of the crack width, something which is more, open for discussion, because that will depend on, if it's a very aggressive environment, or if it's stress concrete, if it's reinforced concrete. All that is, if it's just a problem of aesthetics. For any crack less than 0.4 or 0.3 millimeter, you don't really see them. 1 millimeter, you will see the cracks. Yes. That might be a problem. So that's limiting the crack width is essential. That's my opinion. The value of the crack width is open for discussion, depending on the specificity of the project, basically, of the structure.
Sure. So just bringing you in, Greg, and then we'll go back to Michael. Greg, having a crack width of 0.2 millimeters max in specifications, you've seen it on projects. What happened? Is that good? Like, is that a good way to do things?
Yeah, I think you've got to understand there's a design crack width, and then there's the in the field when things don't go to plan crack width. So ideally in design you've allowed for a crack width, and now that may be, and that's largely around crack opening, underload, flexural crack widths, which we'd determine as good crack widths. They limit. You're not expecting to exceed those at cover depth, and you still expect to provide the durability because you're going to limit the ingress. And those widths are based on the nature of the structure, its location, the exposure environment. So there's a variety of numbers, and whether that's 0.2 or 0.3 depending on environment, and those fairly typical for durability. Again, a lot about what we're talking about here is unplanned cracking. So it's occurred in the construction phase and it's not what you wanted. So you're back to the same sort of principle, depending on the environment and what it is, whether you'd have to decide whether or not that warranted remedial works and repair or not, and then what type of repair depending on the nature of the crack.
Thanks, Greg. Michael, you still got your hand up?
Yeah, I just had a follow-up question for Arno, Dax. So, Arno, with the work you did on the ring test, it showed pretty clearly that the autogenous shrinkage was a key driver for early cracking behaviour. Have you considered whether a different geometry might have a different outcome?
Well, if it's a very different geometry, there's probably some temperature, involved, and because those rings are quite narrow, so that's why we want to use small rings. Another assumption is that the shrinkage and stress are constant across the cross section. So if you start to increase that thickness of the ring, that assumption might be wrong. So that might change the results. In terms of time to cracking, but I would hope that would not change, the outcome of the test in terms of comparing the different concrete. They should be similar. We haven't tried to do it. I know there's an ACM standard with using a much bigger ring, concrete ring. But yeah, that could be checked, experimentally. But I'm hoping that it will not change much the result. Really.
Thank you.
Happy to take any other questions. We have about 5 minutes, because of all the issues that we had. But so any questions that are there. But look, while we're waiting, I'll ask another question of both our speakers. Both of you have been, I suppose, quite negative about the use of the AS1012 Part 13 test. Is there should we be discarding it? Should we be still using it? What's your view? I know you first and then Greg, and then we'll go to Jeff.
My view will be that because that's shrinkage, drying shrinkage test is not a drying shrinkage test, because there's a lot of autogenous shrinkage happening between 7 days and long term, can be a large percentage. So I don't think it's correct anyway to use the term drying shrinkage. So the easiest way to fix that is to start, measuring at 1 day and call it total shrinkage, and then implement an autogenous shrinkage test that we have already, and wrapping the specimen using those self-adhesive L foil, which are waterproof and keep all the moisture in the specimen. So you could measure an autogenous shrinkage and a total shrinkage, and that would be much better than this drying shrinkage test. Also, at long term, there's still a meaning. What you get from the 10, 12, 13 is meaningful if you look at long-term shrinkage. It's not a bad test. That's what I mean.
Sure.
But not for early, just for sure.
Okay, Greg, quickly, and then we'll go to Jeff.
Yeah, no, very good. I think there's the misapplication of a test. So in other words, as I was trying to explain, using the shrinkage test as a proxy to try and get low shrinkage concrete is not really how it works. And then, the origins of the test go way back in time, but it seems to be more a fact of a test to try and prevent the use of poor or unstable aggregate rather than, assess the shrinkage of your concrete per se.
Thanks, Greg. Jeff, can I pass on to you?
Yeah, thanks, Dak. Arnold, one question for you. In your ring studies, did you find any clear evidence in the width differences of the cracks between the fly ash, the OPC, and the higher MPF? Because there was a very clear difference in, obviously, the fly ash versus the OPC and slag mixes. but were the widths also showing similar characteristics or vice versa?
So the ring is not reinforced. There's no steel bar. So as soon as the the tensile strength is reached, it's really breaking. There's no width control through steel. So that's the first thing. But we did see that the crack width of the fly ash was much smaller. It's actually the fly ash concrete that's the only one where we could see some more micro cracks that are propagating and merging together, as opposed to a clear, gap between the two crack faces that we saw in all of the concretes we tested. So fly ash, we did see a difference, even if there's no reinforcement. I'd say the failure mode of the concrete ring was quite different for the fly ash, which is linked to the long time to cracking as well.
Thank you.
Thanks, Jeff. Any last burning question? Anyone? Look, I think that given the amount of interest that has been generated in this by this seminar or this workshop, first of all, thank you to Smartcrete for staging it and everything. Second thing I think is that I want to thank the speakers, and I'm particularly interested, Arno, in your research as it goes forward, because clearly I think there's going to be some very useful things that are going to come out of it as you continue on this work. So, which I'm sure, and I'm hopeful that Smartcrete, we'll have more of these types of events in terms of just looking at this issue, which is just very, very important for the industry. Natalie and Sean, can I just look? I'll close this off here, but before we do that, it might be opportune for one of you just to talk through if people have questions that they want to post after the seminar. You offered a facilitation type thing, Natalie? If you can just articulate that'd be great.
Thank you, Natalie. May I cut in just a little bit, just because Professor Rangan is still with us. I just want to hear him. Professor Rangan, I'm sorry to put you there, but do you want to have to say maybe a few words?
Oh, thank you. I just came to learn and relearn again so that I can start my life again.
Thank you.
It was a very, very interesting presentation. I very much liked it and trying to learn much more. So thank you very much. Thanks for your kind attention. Thank you. I very much enjoyed seeing all of you.
Thank you for joining us. Yeah,
yes,
thank you.
Many old mates and new mates. Thank you.
Thank you so much. Yeah. Okay, Natalie, if you don't mind, yes, for the contact detail. Yeah.
Yep. Please. So I'll just pop our contact details into the chat. If you have any further questions for our speakers, you can email info@smartcrete.com.au and I will forward them to the speakers, or if you have any questions about our events, we'll definitely look into doing another one on this topic, given how important it is. So yeah, thanks very much everyone for attending.
Thank you so much. Thank you, Dak, and thank you to both speakers, Arnold and Craig. Yeah, thank you very much. It's very informative.
Thank you.
Thank you all to participate. Yeah, thank you very much for coming. Yeah, I see you next time. Thank you.
Bye-bye. Goodbye.
Bye.
Everyone.
Bye.